Okay, section 6.4 is two interesting problems. I don't know why I put an apostrophe there. Problems is plural, not possessive. So we're just going to look at the two problems here. You'll notice if you've looked at the homework for chapter 6 yet, there's no homework for 6.4 because I just want to talk about these. So the first one that we're going to talk about is Russell's paradox. And the second one is the halting problem in computer science programming. So Russell's paradox has to do with the history of math a little bit. And at one point, because of how general sets are, they're just collections of stuff, a lot of people thought that all of mathematics could be built from sets. And it turns out that that's just not the case. So all of mathematics cannot be built on set theory. Which is unfortunate because set theory is very general and it lends itself to a lot of aspects. And so as a mathematician named Russell, he realized this and he said, I have a paradox that set theory can't handle because of the way that we define our set algebras and our set properties. So that is the problem he came up with is this, sometimes called the Barbour problem. So if a male barber shaves all males who don't shave themselves, and only those males does the barber shave himself. So I want you to pause the video and just think about this question for a few minutes, not a long time, just a couple, and see if you can figure out what the paradox that Russell discovered was. So if you keep going, I'm going to assume that you've thought about this and you have your answer. So the answer is yes and no. And it's always yes and no. So the way you think about this is if the male barber shaves all males who don't shave themselves, and only those males, well, if he shaves himself, then he shaves himself, but he doesn't shave people who shave themselves. So then he doesn't shave himself. If he doesn't shave himself, well, then he's got to go to himself to get shaved, so he does shave himself. And so you get caught in this loop of paradoxical logic that if you assume yes, then he shaves himself, but by his strict laws here, he's not allowed to shave. He only shaves people that don't shave themselves, so he doesn't shave himself. And if you assume that he doesn't shave himself, then he goes to himself to get shaved, and that's how we go. Now this is a strict logical problem, so obviously we know in the real world there's some things that we could say, some caveats and you know, finer details that we can make this work. But also in math we have other things that can make this work. And so the set theory paradox that Russell's actually famous for, this is one of the examples that gets put in place of the paradox to help us understand. is if S is the set of all sets such that A is a set and A is not an element of itself, is S in S. So what we have is sets of sets, and those sets inside S are sets of sets. So if we have a set of sets, and every one of these sets in our big universal S is a set where they are not sets of themselves, so they don't have themselves in there, is S an element of itself? Well, if you say yes, then S is in S, which means that S is a set such that S is not in S. That's a problem. And if you say no, well then, S is not in S. Why don't I write this down? So yes means that S is in S, which means that S is a set such that S is not in S. Remember our contradiction symbol. That's bad. If you say no, then S is not in S. Well, that means that S satisfies the property for S, so S is in S. And that's the problem, is when we start having sets of sets, which are very much allowed in mathematics. The way set theory is constructed, the way that we build our sets this way, doesn't allow for something like this. And this is just a fun little problem. And this is why we have higher level abstractions in mathematics, bigger than sets, because sets do have structure. So the most abstract thing in mathematics is a really silly concept, silly sounding, not actually silly. And it's just, they're just things. They don't have a lot of structure to them. And almost everything, and I'm forgetting the name off the top of my head right now, but this is kind of the point at which that became necessary. Is everyone was saying set theory is fantastic, we can do everything with set theory. Russell came along and said, not quite, because there's a paradox built into sets. So just a fun little problem. The next one, the next paradox or problem, is probably one you're more familiar with, and that's the halting problem. And this is an algorithms problem. So is there an algorithm that accepts any algorithm and X, any algorithm X and any data set D that will print halts or loops forever. And this would be to indicate if X terminates on D or loops forever. So again, pause the video, take a quick thought about this. Is this possible? Now, most people are familiar with the halting problem in this class, and they're easily jumping to the answer no. And the harder point is understanding why. So the answer here is no, because if x loops forever, then the halting algorithm would have to also loop forever. Because it needs to keep checking values to see if x will halt. Because what if you stop, even if you stop at the billionth data point in D, what if x was going to halt at the trillionth data point or the quadrillionth data point? Well, then your halting algorithm wouldn't have checked everything and it didn't go long enough, so it has to go to there. But then if you say, okay, we're going to halt at the quadrillionth data point, what if it doesn't halt for, another billion data points or another million or even another 2? So you have to keep checking over and over and over. And if you have to keep checking, and I'm saying you as you're the halting algorithm here, well, if x continues to loop on forever and never ends, well, then your halting algorithm would have to follow that loop forever. And so if it's following that loop forever, it's never going to be able to tell you loops forever, because it's just going to run and run and run. And so this is just a fun little problem. The proof is in the book. You can take a look in section 6.4. I don't know if I'm trying to remember off the top of my head. I think they do a less rigorous proof, but they walk through it all with the notion of set theory. But just some fun problems here in the Russell's paradox and the halting problem. Again, remember there's no homework in 6.4. I just like talking about these problems. They're fun and they're interesting. So that's the end of chapter 6.